Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 7. We are in part 2 of chapter 3, and we are discussing ANOVA and design of experiments. Last time we started talking about one-way ANOVA. This is the case when we have more than 2 levels of interest, or you could say 3 or more levels of interest, or if there are several factors of simultaneous interest. One example of this might be the response to drugs, and so one treatment would be one drug, another treatment, another drug, another treatment, a placebo, another treatment, another drug. And so that is an example of when we have several factors of simultaneous interest, and they only have one level each. So this would apply in that case. We talked about the hypothesis statement, and depending on how much you know about the problem or project, you may do the hypothesis statement first. That may be something that you want to solve, or you may have to do the model first and then come up with the, based on that, the hypothesis statement. So the practicality of doing this really depends on how much you know about the subject and the goal of what you're trying to achieve. All right, so the hypothesis statement. One way we can write this is that the means are all equal, the null hypothesis. The other thing that we could do is tau 1 equals tau 2 equals ... equals tau A. That's a perfectly acceptable way to write this. And then our alternative is that any two means are not the same. And that's the way we can write that right here. Any two means not the same. We could also write it at least two means are different. And so these are equivalent statements here. They're saying the same thing. Or we could write this in terms of treatment effects, and that would be that tau I not equal to tau j for some I not equal to j. Okay. And then we have the model, and it can be written in terms of treatment effects or in terms of mu I. And Yij are the observations, the jth observation, the ith factor or treatment level. Tau I is the mean response for the ith treatment level. Mu is the overall mean response. So right in here goes the word mean. So it's the overall mean response in the whole experiment. And epsilon ij is the random error of the ijth situation or cell, or the Yij observation if there's only one of them. Okay. And error is normally distributed with a mean 0, and the reason for that makes perfect sense if you can think about it. If I have the error is the deviation from the actual, and so if here is the actual level, we might be above in one case, we might be below in another case, but as we go through and do more and more parts, if we add up all of the errors, they should add up to 0. They should cancel out because the average is in the middle. Okay. So, and it makes sense on the population level as well. And then the errors have a common variance, sigma squared. And if we take the expected value of Yij, we find that the mean in this model, the way it's written here, is going to be the expectation of mu, which is a constant, so you get back mu, plus the expectation of tau I, which is a constant, you get back tau I, plus the expectation of epsilon ij, and the expectation of epsilon ij is the mean of epsilon ij, which we're saying right here is 0. And recall that the NID notation stands for normally independently distributed. Okay? And so if we take the variance of Yij, maybe I need a different color. So if we take the variance of this, then we have the variance of a constant, which is 0, variance of a constant, which is 0, And so the only thing we're left with is the variance of epsilon ij, and the variance of it is given right here as sigma squared. So we end up with the same variance. So so to really understand what I just said, go back to your properties of covariance and variance, and you'll see that using the properties of covariance, you'll see that you actually have, I think, 6 different covariance terms. When you take the variance of this, it's the covariance of this with itself, and then you have to do this with the other two, and then this one with the other two, and then the last one with the other two. And just like you're multiplying or squaring this term, you'll have 2 times, so it'd be mu with mu plus, or I'm sorry, mu with tau I plus epsilon ij, and then you'd have mu with, or actually you'd have, mu with tau I, mu with epsilon ij, tau I with mu, tau I with epsilon ij, and you'd end up with, because these covariances, if you go back and look at the properties, you'll probably understand what I'm saying. You'll end up with the variance of mu plus 2 times the covariance of mu tau I plus 2 times the covariance of mu epsilon j, epsilon ij, plus 2 times the covariance of, let's see, tau epsilon ij, tau I epsilon ij, plus the variance of tau I plus the variance of epsilon ij, and anything that has a constant in it is 0. So this variance of mu is 0. This variance of mu with, or the covariance of mu with tau I, they're both constant, 0. Mu with epsilon ij, mu's a constant, so that's 0. This tau I is a constant, so this is 0. Tau I is a constant, this is 0. So you're just left with the variance of epsilon ij, which is sigma squared. So that is how we get this variance. And then we have the summation from I equals 1 to a of tau I is 0. And when you think about what tau I is, tau I equals mu I minus mu. So it's the difference between mu I and mu. And so if the first one's above and the second one's below, so what has to happen here is that when you add up tau I, you're adding up mu 1 minus mu, plus mu 2 minus mu, plus mu 3 minus mu, all the way up to n, however many you have. And so you have all of these deviations from mu, and they have to add up to 0. And so this is one of the basic assumptions. Now, another way you can say all this is that all the errors, and thus the observations, are independent and normally distributed, and they have a mean of 0 and a common variance of sigma squared. Or you could specify that there's equal variances for all of the I factor levels. The mean of each ith factor level, as we've said, is mu plus tau I, and the sum of factor level effects is 0. That's what this is. So these are in the box here. This is just another way of saying these assumptions. So you can use either of the assumptions, but I may ask you questions at time, or ask you to explain in projects or homework to make sure that you understand, if you use these, what that implies. Okay. And then we said that the objective of the experiment was to model the relationship between, in this case, etch rate and the RF power, radio frequency power, and then to specify the power setting that will give the desired target etch rate. Our response variable y is the etch rate. That's what we're measuring. Then we have these variables that we fixed. We're not going to vary them. We're just going to set them at one value because they're the values we're interested in. This hydrofluoroethane, I think it's called, and then the gap of 0.8, and then our factor, our x values, if you will, or our inputs are the RF power, and there are 4 treatment levels or factor levels, And those four factor levels are 160, 180, 200, and 220 watts. And then our replications, how many times we're going to repeat each experiment. And so each experiment, if you will, is the power setting in this case, because there's only one variable. So for each level of the power. And we're going to do 5 of each. And that is what we have here in the data. So for each of these factor levels going across, we have 5 repeats or replications. And so we've gone and totaled and averaged. So divide this by 5 to get the other. Okay? And we looked at these box plots and saw that the general trend is upward. As the power increases, the etch rate increases. And the dot plot shows the same thing, but maybe not as well as the box plot, that we have this general upward trend. So you could use either one. I rarely see the dot plot. I more often see this box plot in practice. And then I've gone over all of these assumptions, except now we've changed out I with our experiment. I equals 1 to 4, J equals 1 to 5. It's the ith power level. And then we've switched out response with etch rate, and the factor level with the power level. And everything else stays the same, except, of course, when we talk about power levels instead of, and power effects instead of factor effects. So, looking at the notation, let's recall that Y11 is a Yij. So the first number here, first subscript, is the level. And the second number is the observation. Okay? And so we've got treatment level 1. And so the first number in all of that row is always 1. And then we count up from 1, 2, up to n. 1, 2, all the way up to n. Okay? And when we add them, we say that it's y1 dot, because we added across the j's. So when we add across the j's, then we put a dot there to say that we've summed across that index. And this last one is still missing the dot after the a. And then when we take this value and divide by n in this case, because there's n of them, we get the average, y1 dot bar. And the same thing for all the others, down to y a dot divided by n in this case, which gives us y a dot bar. And then when we sum all of these totals here, so the y I dots, we sum all of those, we're summing across I now. I equals 1, I equals 2, I equals a. And so we've now summed across the j's to begin of all of these. And now we're summing across the i's, and that gives us a grand total, y dot dot. And when we divide by the total number of observations, we get y dot dot bar, the grand mean or the overall mean. Now, for each of these parameters, we need to know how to calculate them or estimate them. And so mu I is the mean of the ith treatment level. And so it makes sense that the estimator is going to be yi dot bar. And I've given you a formula here, which I won't go into the details. I assume at this point you're able to understand the formulas. Mu is going to be estimated with the overall or grand mean. And so I've given you a couple of different ways to look at this. One is if you're using the individual observations, and another if you're starting with the yi dot bars. This works only because we have equal sample sizes. If we didn't have equal sample sizes, this formula would not work for you. And in fact, you'd have n sub I up here and n sub I here, and you would not average these this way. You would add everything up and then divide by a times ni. All right. And then we have before I go there, let's not skip tau I. So tau I, again, is mu I minus mu. We're estimating mu I with yi dot bar and mu with y dot dot bar. So we substitute in for that, and this is our estimate of tau I. So we would call this tau I hat, is what we would, how we would represent that symbol. I should have put that in there, but I forgot. And then for the common variance, we're going to use the pooled variance, but now we're expanding from the two sample case to the A sample case. And so if you recall that S sub p squared for 2 were n1 minus 1, S1 squared plus n2 minus 1, S2 squared all over n1 minus 1 plus n2 minus 1. Now, when we multiply, remember that S1 squared is fine, equals 1 over n minus 1 sum of yi minus, or y1j minus 1 y1 dot bar quantity squared. So when we multiply by n1 minus 1, we're left with this summation here, okay? Which is what we see here. And the same thing for the second term. n2 minus 1 times s2 squared leaves us with the sum of squares there. And then on the bottom we have, even though this simplifies to n1 plus n2 minus 2, when we start expanding this to more than 1, we'd have n1 minus 1 s1 squared plus n2 minus 1 s2 squared plus n3 minus 1 s3 squared plus dot 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 plus sa squared, skip the na minus 1 sa squared. And then this whole thing would be by the sum of ni minus 1, I equals 1 to a. And so if they're all equal, okay, if all the ni's are equal, then this term would be the sum of n minus 1 from I equals 1 to a. They're all the same. That would be a times n minus 1, which is an minus a. An is capital N in this case. And that's exactly what we have here. Okay? So this pooled formula is just pooled variance formula is just a generalization of the two sample case. So if you know it, you can get there from here. All righty. Now, ANOVA. ANOVA stands for Analysis of Variance. So we're going to be analyzing the variability of the experiment. And so how we do that is we're going to partition the variance. And we're going to do this in order to find the test statistic. So far we've gone over the hypothesis statement and the model that we're using, and the second step after the hypothesis statement is the test statistic. So we're wanting to find the test statistic for this experiment. And we're going to do that by analyzing the variance. And we'll see how when we get to the end of this. So the total variance is the total sum of squares. The total sum of squares is the of error, or of sum of squares of the difference from the mean. When we look at, for say, any x, s sub x squared is equal to 1 over n sub x, we can say, sum of xi minus x bar quantity squared. This is the mean of the x's, and these are the individual values. Well, now we have yij and the overall mean of the whole experiment. So the total sums of squares is going to be subtracting each Yij, each observation from the overall mean from the whole experiment. And so we're going to now use a nice technique or trick, if you want to call it that. Most professionals dislike it when I call it a trick. Most mathematicians and statisticians, they don't like to think of it as a trick, but as a technique. And it is a technique, but I think of it as a trick. That's just how I think of it myself. So however you want to think about it or say it. So what we do is we're going to add 0 within this sum. We're going to do that by adding yi dot bar and subtracting yi dot bar. This is all within the square. This is inside of here. And so if you add this all up, you're going to cancel those yi dot bars out and end up back here. Of course, don't do that. We added it in order to be able to utilize it and to simplify or to do something so we can understand something from it. And then the authors leave all this space, all these steps in between here, because it's not obvious. You say, well, why isn't it obvious? It looks obvious, Mark. It looks like, we have this and we have this and there's a plus and now there's still a plus. But look at this. The squares have been broken up too. And you know that the sum, or you know that a minus x quantity plus b minus y quantity total squared is not necessarily equal to a minus x squared plus b minus y squared. In general, that's not true. Okay? But because we're doing that with the means, we end up canceling it out. And so I'll show you that in a minute. But right now, what I want to show you is that when this gets simplified, in this term we have n times and then yi dot bar minus yi or y dot dot bar. And so this is the difference of the this is an estimate of tau I, or the treatment effects. And then this is within each treatment. Okay, so the sum of squares of difference within each treatment. And so that's what this part is. And then we're summing each of those. That's what we're doing with the I. So you can think about this. You can nest one of these summations inside the other. It actually is, even without the brackets, but it may be easier to think about it this way. So you're calculating s sub I squared here, because I is set at some value of I. It's constant for both of these. And then all that's happening in this summation is j is changing. And so this is going to end up being the sum of si squared. Okay. Whereas this is the sum, this is n times the sum of tau I squared. Okay. And so we call this the treatment sum of squares, and this the error sum of squares. The variation within a treatment, that variation is just error. How much each of these depart from the mean. Okay? And so we now need to prove this statement, that this is actually true. We need to prove this step here. Okay? So let's do that. So we're going to start with this statement. So I've got the sum of yi dot bar minus y dot dot bar quantity. I'm putting the parentheses in there because I'm going to treat this as one quantity, like A, and then plus, like B, yij minus yi dot bar, and then the whole thing squared. So I'm going to treat this as one term and this as one term, and this becomes, we'll keep the double sum, and we'll say yi dot bar minus y dot dot bar quantity squared plus 2 times yi dot bar minus y dot dot bar times the second term. So 2 times the first term times the second term. So yij minus yi dot bar, and then plus the second term squared, right? So a plus b squared equals a squared plus 2ab plus b squared. We're doing the same thing. So yij minus yi dot bar quantity squared. And everything is within the summation. Now that we don't have a square out here over the whole thing, we've expanded the square, we can distribute the summations. Because remember, these summations mean add, and so it's just a way of grouping. It's really just telling us in order to add. I equals, or j equals 1 to n, I equals 1 to a. And so I can distribute that summation across the sum, so I get yi dot bar minus y dot dot bar quantity squared plus 2 sum yi dot bar minus y dot dot bar times yij minus yi dot bar plus sums yij minus yi dot bar squared. Okay, and so what we're saying is that this center term has to go to 0. That's what we need to show. Because if you look at this, here's the first term, and, well, I can simplify this a little bit, can't I? J equals 1 to n. So there are the only index in this term is I. So when I sum across j n times, I'm going to get n of these. What I'm going to end up with, keeping the sum I equals 1 to a. Inside of this, I have yi dot bar minus y dot dot bar for j equals 1. This is j equals 1. But there's no j down in here, so I can't replace anything. So it's going to be just this quantity. Plus yi dot bar minus y dot dot bar. This is j equals 2. And then plus, and it's the same value over and over again. For each value of I, we do this same term n times. So we get yi dot bar minus y dot dot bar. And this is squared. Let's not forget the square. And so this is j equals n. So there's n of these within the summation. There's n of these. So this is equal to the sum from I equals 1 to a of n times yi dot bar minus y dot dot bar. Now I can bring the n out, but these do have, there is an I in this expression, so I can't, and this is squared, so I can't ignore that. So for each value of I, this value could be different. So I can't simplify any further. So this becomes, the first term becomes I equals 1 to a yi dot bar minus y dot dot bar squared. Okay. All right. So I'm going to erase this because it's actually something that you hopefully can do very quickly from now on. If you don't see, here I've got this sum. I'm going to put a bracket here. And I've got this sum across j, but there's no j. And there's n of these sums, so this is going to equal n times yi dot bar minus y dot dot bar squared. Okay, so that simplified that, and then I have plus 0, and then plus I equals 1 to a, j equals 1 to n, yi minus yi dot bar squared. I cannot simplify this summation because I have an I and I have a j, and I have an I here. So I have an I twice and a j in there, so there's no simplification of this summation. So I need to show that this is true. So, and if this whole thing is 0, then that means that the sum yi dot bar minus y dot bar times yij minus y dot, or yi dot bar is equal to 0, because 2 times 0 is 0, and 2 will never be 0. So 2 times 0 is 0. So this is what I need to prove. So let's do this. Okay? So now this is j equals 1 to n. This is I equals 1 to a. The first thing I do is I look over here. This one has both an I and a j in it. I can't do anything with that. But this one has only an I. So what I can do, I'm going to call this C for center. And so C is going to enter. So I can move this in front of this summation because there's no j there. Now, I can't just move it all the way out to the end, and I can't move this one before the j, but I can factor out this because it doesn't have any terms of j, right? So for this inner summation here, for every term, we're going to have this quantity multiplied by a different quantity here because this will be a different j. In other words, we'd have yi dot bar minus y dot bar times y1 or yi1 minus yi dot bar. This is for j equals 1 plus, and then we have yi dot minus y dot bar times yi2 minus yi dot bar. And it would keep going. And if we did this for, let's do this for I equals 1. Because it doesn't matter, they'll be different, but yeah. So I equals 1, and then we'll have j equals 1, and so we'll have y1 dot bar minus y dot bar times y1 1 minus y1 dot bar. That's for that one. And then plus, this will be for I equals 1 and j equals 2. So we'll have y still 1 dot bar minus y dot bar times y1 2 minus y1 dot bar. J just went to 2, I stayed the same. So so we have I equals 1. So for all of these, while I is 1, we're going to end up with this term multiplied by this changing term. But this term is the same, so we can factor this out. For the nth one, this is going to be y1 dot bar minus y dot bar times y1n minus y1 dot bar quantity. And so I have this constant value here for all these terms. I can factor it out. And so that's what we're doing here. We're factoring it out because it doesn't have a j. So this can be rewritten, sum of I equals 1 to a, yi dot bar minus y dot bar, sum of yij minus yi dot bar quantity. J is going from 1 to n. Now, here, what I have is, this is going to be, let's say, again, I equals 1. Then we would have y1 1 minus y1 dot bar plus y1 2 minus y1 dot bar plus y1n minus y1 dot bar. And I have n of, this is j equals 1, j equals 2, up to j equals n. So there's n of these terms. And so I have y11 plus, these are all positive, y12 plus y13 plus all the way up to y1n. And then I have minus, and there's n of these. These are all the same. minus n times y1 dot bar. And so this can be written as the sum of y1j from j equals 1 to n minus n times this, and this is 1 over n, sum of y1j from j equals 1 to n by the definition of y1 dot bar. We gave you that estimate in the previous slide. And so this n and this n cancel, and I'm left with the sum of y1j minus the sum of y1j. j equals 1 to n, j equals 1 to n. This minus itself is going to equal 0. Okay? Now here's how we do this. So I'm showing you intuitively, and actually I'm showing you by breaking up it detailed so you can follow along and see that what I'm doing with the summations really is true, that I'm not just waving my hands at this. So this becomes the sum yi dot bar minus y dot bar squared plus the double sum. I can pull the 2 out in the front, so I will because it's a constant. There's no index of it. And I've got a double sum, and again, there's no j here, so I can just move this I equals 1 to a. So I can put this as yi dot bar minus y dot bar sum j equals 1 to n. I have to leave yij inside that summation because there's a j. Okay. Plus, a little messy left there, plus the double sum yij minus y dot bar squared. I equals 1 to a, j equals 1 to n. And now I'm going to show that this is equal to 0 so that the middle term goes away. So then I would say I equals 1, j equals 1, I from 1 to a, j from n, actually I'm going to say that this is the sum. This sum, again, there are no i's in this. This is a dot, that's a dot. And so there's no j here, so there's going to be n of these terms inside this summation. So I can just look at this and say this is n times yi dot bar minus y dot bar quantity squared plus, and I've got 2 sum of over I from I equals 1 to a of yi dot bar minus y dot bar. And then I'm going to distribute this summation, sum from j equals 1 to n yij minus, because there's no square or cube or anything there, I can do that, minus the sum of yi dot bar, and again this is cross j from over j from j equals 1 to n, and then plus this last term which can't be simplified without making a mess, and we're not going to do that. It's not worth it. This is actually the easier formulation. In sum I equals 1 to a yi dot bar minus y dot bar squared plus 2 sum over I 1 to a, not 9, a yi dot bar minus y dot bar quantity, and then I've got sum of yij minus the sum 1 over a, or 1 over n, sorry, that's plugging in the definition for yi dot bar. No, I'm not yet, I'm sorry. So I always forget that I need to go n times yi dot bar plus the last sum, yij minus yi dot bar squared ANIJ. And in sum yi dot bar minus y dot bar squared I equals 1 to a plus 2 sum I equals 1 to a yi dot bar minus y dot bar times the sum of yij. This is across n minus, now I substitute in, this is n times 1 over n sum j equals 1 to n yij, then plus the last term, the last summation, and then in sum I equals 1 to a yi dot bar minus y dot bar squared plus 2, that sum yi dot bar minus y dot bar I equals 1 to a here, and then I've got sum of yij minus the sum of yij plus the double sum yij minus I dot bar squared an, and this is 0, so this gives us in sum I equals 1 to a yi dot bar minus y dot bar squared plus sum from I equals 1 to a, j equals 1 to n, yij minus yi dot bar quantity squared, and this is SS treatment plus SSE. And that is the proof. So I know I did a whole lot of extra explanation. I hope that helped you. So please make sure that if you need to update your formula sheet, do that so it makes homework and projects easier. If you have questions, come to virtual office hours. If you need help before you can come to virtual office hours, by all means, email me. And if you send me a question about a problem, you need to send me a picture of the problem and a picture of your work, so I can see how you're approaching it, and I will be happy to help you, and I'll get back to you as soon as I can. So please take care of yourself and stay safe, because we want to see you next time.